You know, if you have ever had to sit in front of a computer staring at this massive,
Hmm.
just endless spreadsheet, and you find yourself just hitting copy, paste over and over 100 times in a row, you know that exact moment where you start to feel, well, less like a human and more like a piece of office machinery?
Right, yeah.
Your eyes glaze over, your wrist hurts, and you hit this point of, like, existential dread thinking. There has to be a better way to do this.
Yeah, I mean, we build these incredibly sophisticated, powerful machines, yet we consistently trap ourselves into doing the mechanical, repetitive grunt work for them.
Right, exactly.
It is a completely backward dynamic. The machine should be serving us, not the other way around.
That dynamic is actually the perfect jumping off point for our deep dive today. We are exploring the fundamental engine of automation, and that is Python loops.
Yeah, loops are really the core of it all.
And we've got an interesting collection of materials pulling this together for you today. We're looking at some university computer science lecture slides, parsing through logic flowcharts, analyzing how Python structures data using, of all things, the Harry Potter universe.
Which is a great example, by the way.
Right, and we're even pulling apart some classic screenshots from the original Super Mario Bros. Our mission today is to show you how programmers leverage loops to force the computer to do that soul-crushing robotic work.
Yes.
We're going to trace the evolution of logic from making a machine blindly repeat the word meow all the way to how it renders entire interactive video game worlds.
It sounds like a massive leap, right? Going from a simple text prompt to a functioning video game, but the underlying mechanism is actually identical.
Wait, really? I did it?
Totally identical. But to understand how we get to Mario, we really need to look at the brute force method first. When you look at the earliest slide in this university deck, the initial flowchart for making the computer output the word meow is, I mean, it's almost comical. It's not a loop at all.
No, it's just a rigid straight line.
Exactly.
The flowchart starts at an oval that says start, drops straight down to a command to print meow, drops to another meow, drops to a third meow, and then hits stop.
Yeah.
So it's just 3 distinct hard-coded commands.
Which perfectly illustrates the core vulnerability of hard coding. I mean, if you only need 3 outputs, sure, typing it out manually works, but imagine trying to scale that.
Oh, wow.
Right. What happens when your software requires that exact action 10,000 times?
You're spending a week just copying and pasting code. And, like, the file size alone would be absurd.
Oh, absolutely. Not to mention the maintenance nightmare. If a developer decides later that the output needs to be woof instead of meow,
Oh, no.
yeah, they have to manually find and replace 10,000 lines of code. It is a rigid, brittle architecture.
Yeah.
And this is where the concept of the state machine comes in. And the slide deck introduces our first major control structure, which is the while loop.
Right, and the flowchart completely changes shape here. It actually loops back on itself. It introduces a variable, setting a counter I to 3. Then it hits a decision diamond, checking if is not equal to 0.
Mm-hmm.
And if that condition is true, it prints meow, subtracts 1 from the counter, so I becomes 2, and physically routes the flow back up to the decision diamond.
It creates a self-sustaining engine. The code evaluates its own state. It asks, does 2 not equal 0? True. Print meow, subtract 1, now is 1, loop again.
Right.
And the critical moment happens when a high reaches 0. The machine asks, does 0 not equal 0?
Which is false.
Exactly.
Yeah.
That is false. The condition fails, the loop is broken, and the program seamlessly routes to the stop command.
Let me try to ground this for you listening. Think about a parent managing a toddler's Halloween candy stash.
Oh, that's a good one.
You give the kid 3 pieces. That is our initial state, high of 3. They eat 1 piece, and you evaluate the state. Is the candy greater than 0? Yes, the condition holds true. They can have another. And eventually, the candy hits 0. The condition evaluates to false. The candy eating immediately ceases. The loop is broken.
That is a very organic way to visualize it. The action persists while a governing condition remains true. But the source materials present an interesting nuance here. The flowchart we just described counts downward, right? Like 3, 2, 1. However, the subsequent slides offer variations. 1 counts upward, initializing at 1 and checking if I is less than or equal to 3. And then there's a third variation that is particularly important.
Which is initializing at 0.
Exactly. Initializing at 0 and checking if I is strictly less than 3, giving us 0, 1, 2.
Yeah, this stood out to me. Functionally, all 3 variations print the word meow exactly 3 times. The end user watching the screen has no idea which method was used.
Not at all.
So why dedicate slide space to showing different counting methods? Does the hardware actually care if we start at 3, 1, or 0?
Oh, the hardware deeply cares about 0. Oh, yeah. This touches on a fundamental difference between human cognition and computer architecture. As humans, we are conditioned to count starting at 1. We see an object and assign it the value of 1.
Right. 1 apple, 2 apples.
Precisely. But a computer doesn't look at objects. It navigates physical memory addresses. When a computer allocates an array or a block of memory, the index actually represents the offset from the starting memory address.
Okay, wait. So the first position is 0 steps away from the start.
Exactly. The starting address plus 0 is the very first slot in memory. So 0 indexing counting 0, 1, 2 isn't just a quirk of Python or C++. It is the native language of the machine's physical hardware.
Wow. Okay.
Yeah, professional developers default to 0-indexed loops because it aligns the software's logic perfectly with how the memory is actually mapped out on the silicon.
That makes a lot of sense.
Oh,
So we had this while loop, and it
Yeah.
clearly beats the brute force manual coding. But, like, looking at the flowcharts, it still feels a bit dangerous.
House.
Well, you have to manually set the initial counter, define the condition flawlessly, and critically, you have to remember to include that you I one step at the very end of the loop to update the state.
Ah, yes. You've identified the classic trap, which is the infinite loop.
Yeah, I figured.
In a while loop, the programmer is entirely responsible for state management. If a developer gets distracted and forgets to include the code that updates the counter, I remains 3 forever.
Right.
The condition I0 will never evaluate to false.
It just screams meow into the void until the computer catches fire.
Essentially, yes. It will max out the CPU, consume all available memory, and eventually the operating system will step in and crash the program to protect the machine.
Yikes.
Manual state management is powerful, but it relies on human perfection, which, is rare.
Which brings us to the next structural evolution in our sources, the for loop, specifically combined with the range function. This seems designed specifically to remove that human error from the equation.
It absolutely is. The for loop abstracts away all that manual labor of state management. Instead of building the counter, writing the mathematical condition, and incrementing the variable yourself, you just declare your intent.
Right.
You say, for every iteration in a range of 3, execute this block of code.
I'm looking at it like a car transmission. A while loop is a manual transmission. You have to push the clutch, monitor the RPMs, and shift the gears yourself to keep the engine from stalling or redlining.
That's a great analogy.
Thanks. But a for loop with range is essentially cruise control. You tell the car, go 65 miles per hour, and the internal computer handles the throttle, the fuel mixture, and the shifting invisibly.
It's a major reduction in cognitive load for the programmer. The range function generates the sequential sequence 0, 1, 2 in the background, and the for loop automatically iterates through it.
Wow.
It grabs the next value, runs the code, and mathematically guarantees it will stop when the sequence is exhausted. You physically cannot create an infinite loop using a standard range function because the bounds are predefined.
Okay, but let me push back a little. If the for loop manages the state automatically and is so much safer, why ever use a while loop at all? Like, why not just use cruise control everywhere?
Because cruise control only works when you know the length of the road.
Oh, interesting.
Right. For loops require a known finite sequence. But what if you are writing code for a server, waiting for a user to upload a file? You don't know if that will take 3 seconds, 3 hours, or 3 days.
Yeah, that makes sense.
You can't use a finite range. You have to use a while loop. You basically say, while the file is not received, keep listening.
So while loops are for unknown durations, waiting on an event, whereas for loops are for structured, predictable repetition.
You nailed it.
This logic leads right into the flow control keywords highlighted in the slides. We've got continue, break, and return. Let's stick with the driving analogy for a second. If I'm on cruise control with my for loop, things are running smoothly automatically. But if a deer jumps out into the road, I need to take control back instantly. I need a panic button.
And that is exactly what these keywords provide, dynamic intervention. The most aggressive of the 3 is break.
Okay.
When the loop encounters the break keyword, it acts as an emergency eject system. It immediately terminates the loop entirely, regardless of whether there are still items left in the range or if the while condition is still true. The execution jumps completely out of the loop construct.
I can see how that prevents crashes, but give me a practical scenario where I'd intentionally plan to use break in a data operation. Like, why build a loop just to smash out of it early?
Okay, let's scale up. Imagine you are querying a database of 10 million user records to find one specific compromised account.
That's a lot of data.
It is. You deploy a for loop to check each record. By sheer luck, you find the compromised account on the 500th iteration.
Oh, I see. There's absolutely no reason to evaluate the remaining 9,999,500 records.
It would be a catastrophic waste of computing power and time. In terms of algorithmic efficiency, using break the millisecond you achieve your goal optimizes your software. The loop is automatic, but the break keyword gives it situational awareness.
That is super clever. What about continue? If break is the emergency eject, what is continue doing?
Continue is much less destructive. It tells the loop, abandon the current iteration, skip any code remaining in this specific cycle, and immediately jump back to the top to start the next cycle.
So it doesn't kill the loop completely.
No, not at all. It just bypasses the current turn.
Got it. And return. The sources mention it alongside these two.
Return is specific to functions. If your loop is packaged inside a larger self-contained function, return will not only break the loop, it will exit the entire function and hand a final value back to the main program.
Oh, wow.
Yeah, it's basically the delivery mechanism for the result you were looping to find in the first place.
So we've built up this robust engine for repeating tasks safely and efficiently. But loops are pretty useless if they're just running in a vacuum printing, right.
The real horsepower comes when we start feeding them complex data structures. The lecture slides pivot here to demonstrate this, using data from the Harry Potter universe, specifically focusing on the list and dictionary keywords.
This transition is where programming becomes truly functional. Data structuring dictates how loops can interact with information. The sources first introduce a simple list containing 3 strings: Hermione, Harry, Ron.
And based on our zero indexing discussion earlier, I know exactly how the computer maps this. Hermione is sitting at index 0, Harry at 1, and Ron at 2.
Perfect, exactly.
So a for loop could just walk down that sequence effortlessly.
Yes, lists are fantastic for one-dimensional ordered sequences, but the physical world and the data representing it is rarely flat.
Right.
We usually need to map relationships. That is where the dict or dictionary structure comes in.
The slide upgrades the data significantly here. We aren't just looking at names anymore. We have a structure mapping Hermione to Gryffindor, Harry to Gryffindor, Ron to Gryffindor, and Draco mapped to Slytherin. This introduces the concept of key-value pairs. In a flat list, you retrieve data based on its numerical position. In a dictionary, you retrieve the value by querying its unique key.
Wait, so if a list is essentially just reading down a long grocery receipt item by item,
Right.
then a dict is much more like searching your phone's contact list. I don't care that my mechanic is the 45th person in my contacts. I just search the key, their name, to immediately retrieve the value, which is their phone number.
That is exactly it.
Here, the character's name is the key, and the Hogwarts house is the value.
That is the perfect mental model. Dictionaries allow for associative data retrieval, which is incredibly fast and doesn't rely on knowing the data's physical order. The sources actually take this further by showing a multi-column data table.
Oh yeah, I saw that.
Each character has an index, a name key, a house value, and a Patronus value.
And this data table highlights a really fascinating edge case. We have index 0, Hermione, Gryffindor, Otter. We have index 1, Harry, Gryffindor, Stag.
Yeah.
Then we have index 3, Draco, Slytherin. But under his Patronus, the slide explicitly features the Python keyword none with a capital N.
This is such a critical concept in data science and software engineering.
Yeah.
How do you mathematically represent a void?
Right.
None is not a 0. 0 is a very specific integer value. None is not an empty text string, and it certainly isn't the letters N-O-N-E. In Python, none is a dedicated first-class object type.
Ah.
It has a physical footprint in memory, but its sole purpose is to explicitly declare, I am intentionally empty.
So if I'm running a for loop through this dictionary, pulling every character's Patronus for some, visual display, what happens when it hits Draco? If the data is just missing, wouldn't the loop crash trying to pull a value that doesn't exist?
Yes, in lower level languages, trying to access a missing key or a null pointer can cause a catastrophic fault. The system panics because it expects a memory address and finds a void.
Right, it just breaks.
Exactly. By assigning the value, none, the developer is essentially putting up a signpost for the loop.
It's like having a blank page in a book that says, this page intentionally left blank, as you don't think a chapter got ripped out.
Precisely. The loop queries the key, Draco, retrieves the value, none, recognizes it as a valid expected data type, and smoothly continues operating. You can even combine this with our flow control keywords.
Oh, really?
Yeah, you write a condition, you say if Patronus is none continue, the loop instantly skips to the next character without throwing an error. It makes handling massive, incomplete data sets incredibly stable.
Wow, it's amazing how much architecture goes into just preventing a machine from breaking down when it encounters empty space. Let's take all of this, the iterative loops, the flow control, the data structures, and apply it to the final set of sources. Because moving from text to visual rendering really cements how universal these concepts are.
It really does.
The slides end with a breakdown of screenshots from the classic 1980s video game Super Mario Bros.
This is the ultimate synthesis of our deep dive. The environments in video games, especially the classic ones, are not painted. They are mathematically generated by loops iterating over data structures.
Let me paint the picture of these screenshots for you listening.
Mm-hmm.
We see the classic Mario layout, a blue backdrop, but mostly we are focused on the architecture. There are horizontal floors made of brown brick blocks. There are floating blocks containing coins. There are green pipes acting as obstacles.
Mm-hmm.
And as the screenshots progress into the level, we see complex vertical structures, massive staircases or walls made of these blocks, sometimes with specific gaps or tunnels running through them.
When you analyze this through the lens of a computer scientist, you have to factor in the hardware limitations of the 1980s. The original Nintendo Entertainment System had incredibly limited RAM. You were talking about roughly 2 kilobytes of working memory.
2 kilobytes. Wow, you couldn't even save a simple, Word document with 2 kilobytes today.
Exactly. So the developers could not possibly store a massive pixel-by-pixel image of an entire level in memory. It was physically impossible.
So how did they do it?
Well, instead, they stored a tiny library of individual 16 by 16 pixel tiles. One graphic for a brick, one for a cloud, one for a pipe. To build the world, they used loops to stamp those tiles across the screen using a coordinate grid.
Wait, so instead of drawing a floor manually, they just wrote a for loop. Like, for every x coordinate from 0 to 50, render the brick graphic.
Yes, exactly. It acts like a digital typewriter, moving horizontally across the memory array, placing a block at each index.
Okay, that makes sense for a flat floor. But what about the walls and staircases, the more complex vertical geometry?
That requires nested loops. A loop running inside another loop.
Okay.
The outer loop iterates over the horizontal x-coordinates. The inner loop iterates over the vertical y-coordinates. You tell it, for horizontal position 10, run a loop drawing blocks from vertical position 0 up to 5. It generates a column.
Oh, I see.
Then the outer loop moves to position 11, and the inner loop draws another column. Suddenly, you have rendered a solid wall.
This is where the flow control keywords must come into play, right? Because looking at the final screenshots, those walls aren't always solid. There are pathways and gaps carved out for Mario to jump through.
You've connected the dots perfectly.
Mm-hmm.
Inside that nested loop generating the solid wall, the developers insert a logical condition. If the y-coordinate equals 3, continue.
And because we know continue skips the current execution, the rendering engine just skips drawing the block at that specific coordinate and moves on to the next one. It literally leaves a hole in the wall.
Yes. The entire playable landscape is generated on the fly by rapid, overlapping loops, evaluating simple true or false conditions against an underlying grid of data.
It really is mind-bending when you pull back and look at the whole picture. We started this dive looking at a flowchart that simply checked if a counter was greater than 0, and if so, printed the word meow. And the logic driving that simple text output is the exact same foundational architecture used to rapidly iterate across a mathematical grid and render an entire interactive world on a television screen. It's really just a matter of scale and application.
The underlying logic of computer science is universally scalable. Once you master the mechanics of repetition and conditionality, the boundaries are really just determined by the processing power you have available.
Well, let's tie a bow on this journey today. To recap for you listening, we've explored how programming loops rescue us from the inefficiency of hard coding. We unpacked how while loops act as responsive state machines, and how for loops, combined with range abstract, away the danger of manual counting. We saw how keywords like break and continue give our loops situational awareness, and how assigning none prevents massive datasets from crashing the system. And finally, we saw how nesting these loops together is the secret to efficiently rendering the digital landscapes we spend so much time exploring.
It really reveals how heavily our modern world relies on a few core concepts of structural logic. Before we wrap up, though, I think there's a broader implication here worth considering.
Oh, I'm ready for it. What's the final takeaway?
We've spent this time breaking down how machines rely on loops, continuously responding to specific conditions to build worlds and process information. But if you look at human behavior, our routines often resemble organic while loops.
Oh.
Yeah, think about it. We wake up, we commute, we work, we eat, we sleep, and the sequence resets. I equals I plus 1. We execute our daily scripts over and over based on societal or economic
That
conditions.
is so true.
So, if we look at our lives as an iterative process, the question becomes, what is the break condition in your personal algorithm? When you find yourself running on autopilot, what is the specific trigger that forces you to step out of the routine and rewrite the code?
That is a phenomenal question to leave off on. We spend so much time programming our machines, we forget we have to make sure we are just letting our own routines program us. Thanks for joining us on this deep dive. Keep questioning the code, and we'll see you next time.